So in this second part of the compact operators, let us finish the proof where we left over in part 1. So we showed that x phi of n is convergent. So sequence x phi of n is convergent in X. And now, using the fact that the A lambdas are continuous, since the A lambdas belongs to B of X, okay, then the limit of the A lambdas of X phi of n is equal, the limit, okay, is equal to A lambda of the limit, which is y plus z, okay, when n goes to infinity. And again, we have seen that the sequence converges to y, so y is equal to A lambda of 1 over lambda y plus z, which belongs to the range of A lambda. And that is exactly what we wanted to show. We wanted to show that the any element in the closure of the range belongs to the range, therefore R of A lambda is a closed subspace. Okay, the range is a closed subspace. This is not true in general, but so in this second part, we're going to show something really amazing. Okay, so we know that the null spaces of the A lambda n, so notation here, let me introduce notation. So we have the, for every n, for every n greater than 1, including 0 in fact. So we will introduce the space nn lambda to be the null space of A lambda to the power n, and Rn lambda to be the range of A lambda n. Okay? So we have seen before that the null spaces are increasing, finite dimensional, so we have 0. That's the first one, the identity map, is in n1, etc., and n included in nn plus 1, etc. And for the range is the other way around. They are decreasing, and we start with the space, because if you take the first map, which is the identity map, the range of the identity map would be the entire space. It's going to be in R1 of lambda, included, etc., in Rn of lambda, included in Rn plus 1 of lambda, etc. So the null spaces are increasing, and the range spaces are decreasing. Okay, and what's amazing is the following results due to Ritz, okay, theorem, beautiful theorem in fact, theorem. So here, let lambda not equal to 0 and a compact operator. Okay, so here what's amazing is that these null spaces, they stabilizes. They don't keep going and growing. There is at a certain time they are all equal. And the same with these ranges, they start decreasing at a certain time they are all equal. And that's amazing. Okay, so then there exists R S in N such that number one, the nk of lambda is different from nk of lambda plus 1 of lambda. First one are all different. For k from 0 to r minus 1, and after that they are all the same. Nk of lambda equal nk r of lambda for k greater or equal than 1. So before they are different, but then you reach a certain number after which they are all the same. Okay, and that r is the smallest one basically. Okay, 2, and the same happens for the rn's. R k of lambda is different from r k plus 1 of lambda for k going from 0 all the way to s, and then they stabilize this. R k of lambda equals r s of lambda for k greater or equal than s. This is really amazing. The stabilization business is really amazing. Okay? In other words, they don't keep going forever. Okay? Okay, so let us start proof of 1. Proof of 1. Okay, assume not. Okay, that is for every n greater than 1, and n lambda is different from an n plus 1 lambda. Assume that. Okay, so they keep growing and without stopping. Okay, let so n lambda, because they are increasing, is a subspace of n plus 1, and they are all closed. Okay, it's a finite dimensional subspace, and they are all closed. So here, let xn belongs to n plus 1 lambda minus n lambda, such that the norm of xn is equal to 1, and the distance between xn to n lambda is greater than 1/2. I mean, we can have it greater than any theta between 0 and 1, less than 1. So this is one of these beautiful theorems that we have seen before. Okay, we can always have that for any number, but let's take just 1/2. It doesn't matter. 1/2 will do. And you cannot go beyond 1, because the distance from xn to n lambda is going to be less or equal than the norm of xn, because 0 belongs to n lambda, and that's 1. So the distance is less or equal than 1, so you cannot go beyond 1. Okay? But you can go below 1. Okay? So now, let m greater than n, let m less than 1, sorry. Okay? Set x equal 1 over lambda a lambda of xn plus lambda of xn minus a lambda of xn okay? Okay, then x belongs to n lambda. Okay? Why is that? Because xn belongs to n plus 1, xn belongs to n plus 1 of lambda. So a lambda n plus 1 of xn equals to 0, or a lambda n of a lambda of xn equals to 0, which implies, so a lambda of xn belongs to an n lambda. Okay? And also xm belongs to n m plus 1 of lambda, which is a subspace of n lambda, since we assume that m is less than n not equal, since m plus n or m plus 1 is less or equal than n. So the nn, then null spaces are decreasing, and therefore nn plus 1 is in n sub n. Okay? And that's why, since we have a subspace, okay, we get that this vector here, okay, belongs to nn. Okay? Okay, so we have x which belongs to an n, and if we take now, we go back to the calculations, we get that, so lambda x is equal to, and we have to be a little bit careful, a lambda of xn plus lambda of xm minus a lambda of xn. Okay? Which implies that lambda x is equal lambda of xn minus a of xn. Here, of course, I'm using the definition of a lambda plus lambda of xn minus lambda of xn plus a of xn, which implies that this is equal to lambda of xn plus a of xm minus a of xn. So lambda x minus lambda xn equal a of xm minus a of xn. So the norm of a of xm minus a of xn, this is equal absolute value of lambda, norm of x minus xn, and we just said that xn belongs to n sub n, and that the distance from xn to n sub n is 1/2 greater than 1/2, so this will be greater than lambda over 2, which is not equal to 0, uniformly not equal to 0. So the sequence a of xn, okay, will have no convergence subsequence. Okay, contradiction with the compactness of A. So what does that mean? It means that there exists at least a P such that n sub P plus 1 of A lambda, of lambda, because we introduced the notation of lambda, equal the null space of A lambda P here, okay? So let R to be the smallest such integer. So it's very easy. You start from P and you go, what about P minus 1? Yes? No. what about p minus 2? Either we have equality or we don't, but we only have p steps, okay? And therefore, we go down, we're going to reach a level where we have nr plus 1 of lambda equal nr lambda. So here, for any k from 0 till r minus 1, we're going to get that n k plus 1 lambda is different from nk lambda, and n of r plus 1 of lambda is equal to n of r lambda. So this is clear. Okay, starting with p, we can go down, check all of them. There are only p of them. And we come up with this. Now what we need to show now is that, in fact, if you take, so let now n be greater than r. And what we have, okay, we have that nr of lambda is equal to n of lambda. And in fact, we can assume that n is greater than r. So, in other words, we don't have just n equal r because we know that's true, but let's go for n bigger than r, okay? We know that nr lambda is a subspace of n lambda, okay? Let x belongs to n lambda. Let us prove that x belongs to nr lambda. Okay. So what do we have? We have a lambda n of x equal a lambda r plus 1 of a lambda n minus r minus 1 of x equals 0. So the vector a lambda n minus r minus 1 of x belongs to n of r plus 1 of lambda, which is equal to n of r of lambda. So a lambda r of a lambda n minus r minus 1 of x is equal to 0. In other words, a lambda n minus 1 of x is equal to 0, or x belongs to n minus 1 of lambda. So what you do? Now, you show that if n is bigger than r, that x belongs to n lambda belongs now to n minus 1. So you continue now. If n minus 1 is bigger than r, you're going to be in n minus 2, etc., till you reach what? R. So, okay. So x will finally arrive to nr lambda after a finite number of steps, which shows that the two spaces are equal. So next, let's go to the range now. Okay? So now, proof of the second part of the theorem. So let us prove. Assume that r n plus 1 lambda is different r n lambda for any n greater or equal than 0. Assume that. They are all different. Okay? And we want to get a contradiction here. Okay? We showed before that the ranges are all closed subspaces. Okay? And that these subspaces are decreasing. So r n plus 1 of lambda is a closed subspace of r n of lambda. Okay? Let yn belongs to Rn lambda minus Rn plus 1 of lambda, such that the norm of yn is equal to 1, and the distance, as we did before, from yn to Rn plus 1 of lambda, this is greater than 1/2. Okay, so now let m and n two positive integers, let m less than n. Okay, so we have let z equal 1 over lambda time a lambda of ym plus lambda of ym minus a lambda of yn. Okay, so what do we have? So lambda z equal a lambda of ym plus lambda of ym minus a lambda of yn. So the yn belongs to Rn, okay? Plus 1. So yn belongs to Rn. So a lambda of yn belongs to Rn plus 1. Okay? But because they are decreasing and n is bigger than m, okay, so m plus 1 will be less or equal than m. So m plus 1 is going to be less or equal than n. So this will imply that, okay, which implies that Rn lambda is a subspace, because they are decreasing, subspace of Rm plus 1 of lambda. Okay? So yn is going to be in Rn, and a lambda of yn will be in Rn plus 1. Okay? So it's going to be subspace yn. So yn is one little mistake. This is not m. This is n. Sorry. We're taking this vector here, n. Okay? So yn is in Rn plus 1, but Rn plus 1 is a subspace of Rn, which is a subspace of Rn plus 1, and a lambda of yn, yn is in Rn, a lambda of yn will be in Rn plus 1, which is a subspace of Rm plus 1 as well, and a lambda of ym, ym is in Rm plus 1, and a lambda of ym will be also in Rm plus 1, because they are decreasing anyway. All the numbers that are bigger than n plus 1 will stay in Rn plus 1. Sequence is decreasing. So here, this tells us that, so if we use now the property of what is a lambda, we get lambda z equal lambda ym. We have to be very careful. A ym plus lambda yn, and now definition of a lambda yn, and that's why I had to correct myself, plus a of yn. Okay, so this simplifies and we get lambda ym minus a ym plus a yn, which implies that a of yn minus a ym equals lambda times z minus ym. Okay? So the norm of a of yn minus a of ym, this is equal absolute value of lambda norm of z minus ym. And since z belongs to Rn plus 1 and the distance from ym to Rn plus 1 is greater than 1/2, this is greater than absolute value of lambda over 2, which is not equal to 0 uniformly of n and m for any n and m. So the sequence a of yn has no convergent subsequence. Okay, contradiction again because a is a compact operator. Okay, so this tells us what? That there exists a p such that r of p of lambda is equal to r of p plus 1 of lambda. Okay, so what we do, we take S, let S be the smallest, such that integers such that R S of lambda equal R S of lambda S plus 1, sorry. Okay, so we know that for any k less or equal than S minus 1, we have R k of lambda different from R k plus 1 of lambda. Okay, that's before the fact, as I said, we can check it out till we reach the smallest one. So the ones before are all different. And now let n greater than s. Okay? Okay. Let us prove that let's prove that R of n lambda equals R of S of lambda. So the sequence stabilizes, in other words. They are decreasing and then it reaches S, and then after that they're all the same. Okay? Great. So since the sequence is decreasing, we know that so we have okay, R n of lambda, which is smaller, okay, than R s of lambda. Okay, so n is bigger than s. So what we're gonna do is we're gonna get n minus 1, okay, and show that we have, okay, let's do it. So let x the other way around now belongs to Rs of lambda. Since Rs lambda equal Rs plus 1 of lambda, then x is belongs to Rs plus 1 of lambda. In other words, we have there exists z in x such that x is equal to a s plus 1 lambda of z. Okay, but a lambda of s, here we get what belongs to our s of lambda, okay, equal to our s plus 1 of lambda. So there exists another point z2, z1, okay, in x such that a lambda of z is equal to a lambda to the power s plus 1 of z1. So x is equal to a lambda 2s plus 1 of z1. Okay? Okay, there was a little mistake right here. So what we have in fact is s. So a lambda s of z belongs to Rs, which is, so there exists a z1 such that a lambda s of z equal a lambda s plus 1 of z1. And this will imply that, sorry, so we have to change this a little bit. So it's going to be s plus 1, s plus 1 plus 1 of z1, or a lambda of s plus 2 of z1. So in other words, x belongs to r s plus 2 of lambda. So you see, it is in rs, then we have rs plus 1 because it's equal to rs, and now we have rs plus 2. So we keep going, so we can next, so the same idea here. So we have a lambda s of z1 belongs to r s lambda equals to r s plus 1 of lambda. So there exists z2 such that a lambda s of z1 is equal to a lambda s plus 1 of z2, which implies that x is equal to a lambda s plus 3 of z2. So you see, we can keep going all the way till, so this of course means x belongs to r s plus 2 of lambda, and we keep going till x will belong to r n of lambda, because n is bigger than s. So you keep coming, s plus 2, s plus 3, s plus 4, till you reach what? N, and this will imply that x belongs to Rn, or that Rn of lambda is the same as Rs of lambda. So they are all the same. Okay? So this shows the stability of these subspaces. And the next result for the next theorem, so we have this S for the stability integer S for the ranges, and the stability R, the integer that stabilizes the null spaces. Okay, great. So now what we're going to show, the ultimate result, we're going to show that N and S are in fact the same. But before we do that, we need some technical lemmas. So lemma, okay, lemma, okay, let A be a compact operator of X, X being a normal vector space as usual. Let lambda not equal to 0, okay, for there exists Okay, there exists a number m positive such that for any y in the range of a lambda, okay, there exists x in x such that y is a lambda x, and there is some control over okay. So here look at this as being a linear equation, and we will see more of these later on. Look at this here as a linear equation, and you are given the y and you are trying to solve for x. So of course we do have it if y belongs to the range. This is a sine qua non condition. You need to have that. Once we have that, so there exists an x, you want to have some kind of control or stability of the solution x. Okay, so that's why you have that condition norm of x less or equal than m times norm of y, and this is independent of y. The number m only depends on the operator. Okay, so really an interesting problem here. Proof, okay, that x belongs to the range, okay, and set delta x to be the distance from x to the null space. Okay, just for the sake of to clarify this, because some people may be a little bit lost and will not see exactly what's going on. What does it mean, this delta x? And this delta x, in fact, which is the infimum, okay, the infimum of the norm of x minus z in the null space. Okay, so pay attention to this. If z belongs to the null space, and if x solves the equation that you have in this red box here, okay, is a solution to that, a lambda x equal y, then if you add to it a z from the null space, it's going to be also a solution. So a lambda x minus z will also be equal to y as well. So it's the problem is invariant by adding any vector in the null space of the solution. So the solution is one particular solution x, and you add to it the null space, okay, of a lambda. And if that's the case, you want to control a norm of x that's equal to m norm of y. You want to control that norm of x of the solution. So you want to take the smallest one, the infimum of all these ones, and that's why we have this, okay? Which is, by the way, just if you look at the quotient space, and this is just the norm of the class of x in the space x divided by the quotient space of n a lambda. So you see, it's invariant by n a lambda, and that's why we can consider the quotient space and solve it there. The linear equation can be transposed into the quotient space, and now we have just the norm of the class. That's exactly the delta x. So delta x should not be seen as something out of the ordinary or weird, okay? It's just a normal stuff. So let us first prove that, that there exists there was one tiny mistake. I mean, because I was talking about x being the solution, this is wrong, and it should be in x. Okay, so here this is x in x. Okay, so there exists m positive such that delta x is less or equal than m, the norm of a lambda x. Okay, so let us prove this. Okay, assume not. Assume not. Then there exists xn in X such that, okay, delta of xn over the norm of xn, a lambda of xn, sorry, a lambda of xn, a lambda of xn, this is greater than n, which means that it goes to infinity, okay? Because you can't find that for every n. Okay, great. So here, this implies that xn does not, so clearly xn does not belongs to the null space of a lambda, because I don't want xn to be the delta xn equal to 0 anyway, so this is not equal to 0, okay? And so this will give us, and we know that n of a lambda is a finite dimensional space. That's what we proved previously, finite dimensional vector space. So there is an element, so there exists W in n of a lambda such that delta of xn is equal to the norm of, this is of course n here, so it depends on xn minus wn. Okay, this is for every n. So now let Zn be xn minus wn over the norm of xn minus wn. So, which is the same as 1 over delta of xn times xn minus wn. Okay? So the norm of Zn is 1. Okay? Okay? And a lambda of Zn equal 1 over delta of xn, a lambda of xn minus wn, but don't forget that wn belongs to the null space of a lambda, so this is just a lambda of xn divided by delta of xn, which is a positive number. So the norm of a lambda of Zn is equal to the norm of a lambda of xn over delta of xn, and since this is 1 over that goes to infinity, this goes to 0 as n goes to infinity. So the limit of a lambda Zn is 0. Okay? Now, a lambda of Zn equal lambda of Zn minus a of Zn, and since the Zns are bounded, there exists a subsequence of Zn. There exists a subsequence Z phi of n such that a of Z phi of n converges to some omega. Okay? Great. So what do we have? We have a lambda of Zn goes to 0. Okay, this one here, this sequence here goes to 0. This sequence here, phi of n, converges to omega. So this will tell me that, so lambda z phi of n. I'm sorry. Let's move lambda out. Z phi of n, which is equal to what? To 1 over lambda time a lambda of z phi of n plus a of z phi of n. Okay, so this one goes to 0. This one here goes to 0. This one goes to omega. So we conclude that z phi of n, so limit exists of z phi of n, and is equal to 1 over lambda times omega when n goes to infinity. So in this case, we get, again, because we said that this here goes to 0, hzn, so we get that by taking a lambda of z phi of n, which goes to 0, we get that 1 over lambda, a lambda of omega equals 0, or a lambda of omega equals 0. Okay? So in other words, that omega belongs to, so omega belongs to n of a lambda. Okay? This implies that, remember that the omega n belongs to n of a lambda. So if that's the case, then here omega n, okay, so omega n, okay, plus delta of xn omega belongs to n of a lambda, okay, because n of a lambda is a subspace. So the norm of Zn minus omega equal. So what was Zn? Zn was xn Zn xn minus Zn over delta of xn minus omega, which is equal 1 over delta of xn, the norm of xn minus Zn minus delta of xn omega. And we just said that Zn plus delta xn omega belongs to n lambda. So this is greater by definition to the definition of delta of xn, which is the distance from xn to the null space. So this is delta of xn over delta of xn, which is equal to 1. Okay? So we have this subsequence of Zn which converges to omega, and they are all away 1 from omega, contradiction. Okay? So this contradicts, contradiction with limit of z phi of n equals omega when n goes to infinity. Okay? Okay. So there exists, therefore, there exists m positive such that for every x in x, okay, we have the delta of x less or equal than m norm a lambda x. Okay? So now we're almost done. Let y belongs to the range a lambda. Then there exists x in x such that y is equal to a lambda x. And if you follow the discussion I had before, we can add to it any vector from the null space, which is also equal to a lambda of x minus z for any z in the null space. Okay? So now what we have is, okay, so there exists, null space is a finite dimensional space. We know that there exists z1, z0 in the null space such that the distance from x to the null space is exactly the norm of x minus z0. So we have a norm of x minus z0 which is less or equal than m, the norm of a lambda from what we did before, x minus z0, which is exactly m times the norm of y. So for any y, we found a vector such that it solves the equation a lambda of that vector equal y, and it gives us that control over the norm. Okay? So the proof of the technical lemma is done. So now, as I told you earlier, we're going to use this technical lemma to show that in fact R and S are the same, okay? It's a little bit tricky, but so here, let lambda be non-equal to 0. Let A be a compact operator defined on X, okay? So we have seen that the range R n plus 1 is equal to R n lambda for n greater or equal than S. Okay? So now, okay, so in particular, we have in fact, as we said earlier, we said that Rn of lambda is also equal to Rs of lambda for any S. So we have both of these, okay? Great. So now, okay, let X belongs to X. So we know that A lambda S of X belongs to Rs of lambda, which is also equal to Rn for any n bigger than lambda. In particular, is equal to 2s of lambda. Okay? So this tells me that there exists z in X such that A lambda S of X equal A lambda 2s of X, of Z, which implies that A lambda S of X minus A lambda S of Z, this is equal to 0, or X minus A lambda S of Z belongs to the null space. Okay, and S lambda. Okay, so X is equal to A lambda S of Z plus X minus A lambda S of Z. So this vector here, this vector belongs to ns lambda, and this vector belongs to the rs lambda. So what did we prove for every x? Okay, so we proved, in fact, conclusion, x is the sum of rs lambda plus ns lambda. So we have this sum between the two. And in fact, it's a direct sum. Okay, let's show that. Let x belongs to the intersection. Okay, we want to show that this is a direct sum. So we need to show that this intersection is reduced to 0. Okay, so let's take x, which belongs to this subspace. So we know, so x belongs to rs lambda. Okay, so there exists x1 in x such that x is equal to a lambda s of x1. And in fact, because all of the ranges are equal to rs, we can say that in fact for any n greater than 1, okay, x belongs to R ns of lambda. In other words, there exists xn in x such that x is equal to a lambda ns of xn. Okay? So now, we know also that x, since x belongs to ns of lambda, okay, there exists n0 greater than 1 such that x will belong to n0 s lambda, and this n0 s will be greater than r. Okay? Let us go back to the xn. So we said that x is equal to a lambda ns of xn. Sorry, that's not okay. So let's go back to this inequality here. So what do we get? Because x belongs to ns of lambda, so we have ns a lambda s of x equal a lambda ns plus 1 plus s of xn, okay, which is equal to 0, which is equal to a lambda n plus 1 of s, okay? Okay. So xn belongs to n of ns plus 1, n plus 1 s lambda. Okay? Okay. So assume x is not equal to 0. Okay? Then xn does not belong to n of ns of lambda. Okay? So this tells me that n ns of lambda is different from n plus 1 of S of lambda. But when n is, as we said, bigger than, for n large, okay, we are going to have ns, sorry, we're going to have n0 s greater than r, and therefore all of them for that n0, okay, but for n large, okay, meaning like n0, the one we mentioned, we have n of n0 s, okay, lambda equal, if you go farther even, n plus 1 s of lambda equal on r lambda, okay? So therefore this we generate what? A contradiction, because we just said that this they are different, and now we get what? That they are equal to on r lambda. And therefore our x, so x equal to 0, which means that r s lambda intersect ns lambda is 0. Okay? So, conclusion, x is equal to r s lambda plus direct sum ns lambda. Truly amazing. Okay? So now let us look at the properties of A lambda restricted to these subspaces. First, so now we have this decomposition of X into these two subspaces. The range of A lambda S, and the null space of A lambda S. Okay? Let's look at now, it's obvious, okay, that if X belongs to NS lambda, okay, then obviously we have A lambda X belongs to NS lambda. In other words, we have, this obvious, just this is true because NS plus 1, A lambda of NS plus NS is just NS plus 1, and therefore is the same as NS. So that's obvious, okay? And which means that, okay, that A lambda of NS lambda is in NS lambda. In fact, it's equal. Next, in fact, we have equal, not only, okay? So now, if X belongs to RS lambda, okay, then we know that exists Z in X. I'm sorry, no, it's going to be, if you are in RS, such that X is equal to A lambda S of T. So A lambda of X is equal to A lambda S plus 1 of C, okay, which belongs to R of S plus 1 of lambda equal to Rs of lambda. Okay, so what we have here is that A lambda of NS lambda stays in NS lambda, and A lambda of RS lambda also stays in RS of lambda. So these two subspaces, which somehow decompose to space X, they're stable by A lambda. Okay? Great. So now, let us show that the restriction of A lambda, so set A lambda hat to be the restriction of A lambda to RS lambda, because A lambda on NS lambda is equal to 0. And let's take now A lambda, restriction of A lambda to RS lambda. So in this case, what we can see is that it is injective, is injective, or one-to-one, indeed. Okay, let X belongs to RS lambda and assume that A lambda X equals 0. Okay, so obviously this will imply, because so this implies that X, so X belongs to N1 lambda and N1 of lambda, because they are increasing, so X belongs to NS of lambda. Okay, so okay, X belongs to NS of lambda intersect RS of lambda. Again, keep in mind, why do I have X belongs to NS? Because S is bigger or equal than 1, so NS lambda is smaller than N1 lambda. Okay? No, sorry, I confused NS with RS. No, we don't have this, so this is not true. Okay? Because the subspaces NS are in fact increasing. Okay? So let's take this out so we don't get confused. Okay? So we have X, which belongs to, and I don't need, it's not going to help. Okay, so we have that. But let's use the fact that X belongs to RS, though. There exists Z in X such that X is equal to A lambda S of Z. And now we use the decomposition. So we know that this will be of Z1 plus Z2, where Z1 belongs to RS lambda and Z2 belongs to NS lambda. So if Z2 belongs to NS lambda, A lambda S of Z2 will be 0, so X will be A lambda S of Z1. Okay? But Z1 belongs to R S lambda, therefore there exists at Z2 such that this is just A lambda S of Z2 for some Z2 in X. So we have X equals A lambda 2S of Z2. Okay. So A lambda X is going to be equal to A lambda 2S plus 1 of Z2 equals 0 because our X belongs to the null space of A lambda. Okay? So A lambda S plus 1 of Z2, this one here belongs to the R lambda S plus 1 of lambda, and A lambda S plus 1 of Z2 belongs to NS lambda. Since RS plus 1 is equal to RS, so A lambda S plus 1 of Z2 belongs to RS lambda intersect with NS lambda, okay, which is equal to 0. So because it's direct sum, we prove this. A lambda S plus 1 of Z2 is equal to 0. Okay? But since s is greater or equal than 1, okay, we get that, so z2 belongs to rs, I'm sorry, not r, ns plus 1 of z2, I'm sorry, of lambda, which is also equal to, I'm sorry, okay, which implies easily that a lambda, okay, a lambda of s plus s, 2s of z2 is equal to a of lambda s minus 1 of a of lambda s plus 1 of z2 equals to 0. Okay, but as you can see here, we have x equal a lambda of 2s of z2, and this would apply, so x is equal to 0. In other words, the a lambda, as we said here, a lambda hat is injective. So keep in mind, a lambda hat is only defined on Rs of lambda. Okay? Now, as we said also, okay, a lambda, so the range, if you go, so a lambda hat, which is the restriction, the range is, in fact, Rs lambda. So we can see it's very easy to see that since a lambda of Rs lambda is equal to Rs plus 1, lambda equal to Rs, so this tells me that this a lambda hat goes from Rs lambda into Rs of lambda, and it is injective and surjective, so is a bijection. Okay? And remember that Rs lambda is a closed. We proved that it's a closed because if you take the compact, we did it. All the Rn lambdas are closed subspaces of X, and all the Ns lambdas are all finite dimensional subspaces. So this subspace Rs lambda is a closed subspace of X. So we have now a bijection from Rs lambda into Rs lambda. Okay, and what's amazing is now we can use the lemma with X equal Rs. Okay, so here, previous lemma tells us that, so if we take A, now we have, so this is my subspace, so now we know that since A lambda and A commute, this is the same as A lambda, then A of Rs lambda is a subspace of Rs of lambda. Okay? So now we take A and we go from Rs lambda into Rs lambda. The restriction of A into that subspace, okay? So let's call it A hat. A hat is the restriction of A to Rs lambda. Okay? Since A is compact, A hat is compact, and therefore there exists an M. We apply the lemma to Rs lambda. There exists an M positive, not to the space X, to Rs lambda, such that for any Y which belongs to A lambda of Rs lambda, there exists X in Rs lambda such that y is equal to a lambda x, and the norm of x is less or equal than m, the norm of y. Okay, so clearly the x here, because we are taking the restriction of a lambda to rs, so here remember the a hat of lambda is the associated a hat lambda is the same, because lambda I minus, so if you restrict, you stay the same. The identity of rs lambda, basically, the restriction of the identity from x to rs lambda is the identity of rs lambda. So we have this, and we know that r lambda hat is invertible, and that solution x is unique. In fact, this is a equal a hat inverse, okay, of y. So what we get, so the norm of a hat lambda inverse of y is going to be less or equal than m norm of y. In other words, a hat lambda inverse is bounded. So it is a continuous linear place. So the restriction of a lambda to rs, the range, is invertible, but its inverse also is a continuous linear operator. So let me put all this together. We're almost there to prove that R and S are the same. So we have a theorem. Okay. Let lambda different from 0. I'm putting all the results together now. Okay. Let A be compact operator. Okay. So we know let S greater or equal than 0 such that R S plus 1 of lambda equals R S lambda, and R K plus 1 of lambda different from R K of lambda for K between 0 and S minus 1. So in this case, we know then X is equal to RS lambda plus NS lambda. That's what we just proved. So they give me a direct sum of the space. Moreover, this is amazing, beautiful, A lambda restricted to R, if I take the operator, the restriction of A lambda restricted to RS of lambda, then A lambda hat belongs to B, K is compact, is compact in this subspace, and A lambda hat inverse exists and is continuous. In other words, is a bounded linear operator. Okay, so this is all put together. Okay, so now we're ready to prove the main beautiful theorem, the last theorem, the last result. Okay, is theorem, the most beautiful result of all this theorem. So let lambda different from 0, let A be a compact in X, compact operator. So what do we need? Let R and S be as before. So remember, so the S stabilizes the ranges and the R stabilizes the null spaces. Okay, then it's really amazing. Then R equals to S. This is beautiful. and specific to compact operators. Okay? So here, proof. Let x belong to ns plus 1 of lambda. Since x is decomposed, since x equal r s lambda plus ns lambda, then x is equal to x1 plus x2 with x1 in ns lambda and x2 in rs lambda. Clearly we have, so a lambda s plus 1 of x equal a lambda s plus 1 of x1 plus a lambda s plus 1 of x2. But x1 belongs to ns, therefore a lambda s of x1 is equal to 0, and if you multiply by another a lambda, it doesn't change anything, so this is equal to a lambda s plus 1 of x2, and this is equal to 0. Okay, so x2 is in rs, and we have a lambda s plus 1 of x2 equals 0. Since a lambda is a bijection, the restriction, so a lambda hat of s plus 1 of x2 is equal to 0, where a lambda hat is the restriction of a lambda to rs. So this tells us, because it is a bijection, so x2 is equal to 0. Because a lambda hat is a bijection, so a lambda hat to the power of anything is a bijection, and therefore this gives you x2 equals 0. So this tells us that x belongs to ns of lambda. So in other words, and since ns already contains ns plus 1, so what we get is that, so we know that the ns are decreasing, or increasing, so we have to be very, very careful. We know that ns lambda is a subspace of ns plus 1 of lambda. Okay? So this implies, so ns of lambda is in fact equal to ns plus 1 of lambda. Okay? And because of this, we have seen before that when this happens, r is the smallest one, so r is less or equal than s. Okay? Okay. So in order to prove now, s less or equal than r, okay, let us prove that r of lambda equal r plus 1 of lambda. Okay? Okay, we know since the r's are decreasing, we know that r plus 1 of lambda is a subspace of r of lambda. Okay, let x belongs, now we want to prove the other way around, so let us take r of lambda. Okay, then there exists z in x such that x is equal to A lambda R of Z. Okay? And again, same as before, that Z is going to be decomposed again as Z1 plus Z2, where Z1 belongs to NS and Z2 belongs to RS. Okay? Good. So now, since, as we proved, R is less or equal than S, okay, then NS, okay, of lambda is equal to NR of lambda. So, A lambda R of Z1 is equal to 0, which implies from this that X is equal to A lambda R of Z2. Okay, now Z2 belongs to RS lambda, and A lambda hat is a bijection. Okay, so X2 is equal to A lambda of A lambda hat of Z2, sorry, Z2 of Z2, okay, of Z2. Okay, so X is equal to A lambda R times A lambda of A lambda hat of Z2, or X is equal A lambda R plus 1 of A lambda hat of Z2. In other words, this means that X belongs to R plus 1 of lambda, and that tells us again, so R of R lambda is equal to R plus 1 lambda, and that's exactly what we want to prove, and this will tell us that S and R are the same. So it was a little bit a long lecture, 2 parts, part 1 and part 2, almost like a 3 hours lecture. So I hope that you enjoyed it, and thank you very much for your attention.